Hello, everybody. Welcome to week 3 for our game design class. Oh, put the button, my hand in class. There we go. Right, and then okay, a bunch of people coming in all of us. I waited a moment before I started the recording. Wait till everybody's audio kicks on. Okay. Hello, everybody. Welcome to week 3 of advanced simulation game design. This week, we're diving a little bit deeper into physics and probability, some formal math sort of stuff. However, in week 1, we looked at a little bit about physics, just sort of a preview because we needed to use it in our class example. It's kind of like that. The computer's going to do the calculations. We just need to know when to ask for particular things and how to set them up. So a little bit about that to talk about this week. The final project proposal is due this week, so along with the small homework assignments throughout the course, there's going to be one larger game due at the end of the semester with a few more requirements on it that you'll just be working on throughout the rest of the semester. This week is just submitting the proposals. We're talking about that, talk about homework submissions, and the next small assignment is going to be a group assignment, so we need to get set up for those. Yeah, I've kind of gone back and forth. We have a nice number in this class. There's 12 people, so it splits up into groups of 3 or 4 evenly. I could really go either way. Does anybody have any preference? Let me take a vote on it. Would you rather be in groups of 3 or groups of 4? You gonna throw it in the chat or unmute and speak up? Any preference? Okay, there's one vote for a group of 4. Another person abstained. Yeah, I went back and forth a couple times this morning. Actually created the group, so it's like, oh, we're gonna do it a different size. And then I deleted them. Full preference for. It looks like there's more votes for a group of 4, which is nice because you can be up to work more and maybe get a little bit more going in the game if there's 4 people. Did everybody vote? Yeah, I see 1, 3. A couple people could go either way, and several people voted 4. So I guess we can do groups of 4, and at the end of class today, we can kind of use breakout rooms to split up and talk to your group, your teammates for the first time. Let's see, let's get that out of the way. That out of the way. And this time, right before class, I stayed logged into Ivy Learn, so we might have to just log back in immediately. Let's see. I go to assignments. Oh, oops, wrong one. Number 1. But yes, that's fine. A question in the chat. You'll have to make some adjustments to it because the question in chat is on the first project, the student 9, is it okay to use the template movement script with character body 2Ds? Yes, but you will need to make some adjustments to to get the movements correct for what the thing is asking for. But yeah, that you can use that as a starting point. Yeah, if you have anytime you have templates, you can use those as a starting point. Actually, sometime soon, maybe Wednesday, but probably next Monday, we will even look at creating our own templates because those default templates might not be what we do every time, right? Where for people who've used them before, we'll quite often go in there and start with that default template and then make the same changes before we get around to doing anything. So it just makes more sense just to create our own template that adjusts that. Let's see. Okay, this is a group project. So yes, anytime you have templates and things like that to start with, that'll be fine. When it works or when it can be used. Let's see, create a new group set. Well, right before you got here, we voted. There was a vote on the group size. It seemed like most people voted for groups of 4 for the next little project. So what is this? This is group project number 1. Groups. So yeah, it's kind of nice. There's 12 people in this class, so it splits up evenly. That usually doesn't happen. So 3 groups. I'll leave the group leader checkbox off, and y'all can decide that amongst your group. Okay, so and the if you go to the people tab on the roster, you should see a tab for groups, and it would have randomly assigned you to a group. And at the end of class today, we'll kind of set up the breakout rooms there on Zoom, so you can meet with your group and start talking about what the best form of communication for you all will be, or how you want to go proceed with that.
So
What's that?
So it auto looks like it autos.
Yeah. Yeah, I just said put everybody in the group. So there should be groups of 4, right? I clicked the wrong thing, Nick. Yeah. One checkbox, you enter the number of groups, and then the other one you enter the number of group members. So we'll finish that up today. Might as well look at this while we're here. So the assignment is due this evening. First coding project. Hopefully that's going well. Has anybody hit any major issues with that first coding project? Other than just the long amount of time things like that take? Okay, I assume the silence means no major issues with it or anything. Hopefully you had a lot of fun with it. So with the submission, there's going to be 2 submissions. You'll upload all the project files to a GitHub repository, and make sure you preserve the structure, the organization of the folder files inside of the folders. Kind of still needs to be there in order for the game to run. So you'll put go to like the top level project folder, and unless you have more than 100 files, which very easily could happen in a game project. If it's under 100 files, you can use the web interface on GitHub and just drag and drop that parent folder. Otherwise, you'll want to do like we did last week in class, or yeah, we saw last week in class where we opened terminal and choose the push command to send a whole lot of files up at once. So you'll turn that in as well as a video showing you playing it. Some of your classes you might be used to like sending a screenshot showing the program running, but for game we kind of need to see the movement. So there's lots of screen capture software out there. If you haven't seen it before, there is one built right into Canvas Studio. over in the grid navigation link, you should see a button for studio. Or if I go to student view, when you go to submit it, one of the different different tabs here, it might be easiest to make multiple submissions. I will see all of the submissions you make. So you can go to the website URL and paste in the link to your GitHub repository. But if you go to this tab that says Studio, this has screen capture software built in. Screencast-O-Matic, it's one that's been around for a while. They have a free version, the watermark stuff, and then a paid for version. That's a whole lot of nice extra features in it. This is the paid for version, so you can do that and just record the video right here on the submission spot. Might be an easy way to do that. Get the video in there. And also, that's also in like every rich text editor. So if you wanted to do a video for your discussion board, and so one of your discussion board postings, if it makes sense to do a video, I am perfectly okay with that. Break out of some of the traditional text because we can do it a little bit better. So there's that. Got everybody in groups, and at the end of the day today, we'll split up into breakout rooms. That way, y'all can figure out what would be the best way to communicate with each other and set up some sort of timeline. Figure out who the main person in the group is, and you will only need to make one submission for the group. So instead of everybody having a spot where to upload the files, it's set up so that there's just one spot for the group to upload. I guess while screen sharing, can go over this other thing. So the your final project proposal will also be due, or will be due next Monday. Just come in here. I'd recommend maybe taking a day or two to figure out what sort of game you want to make. A good place to maybe start looking as you're figuring out what to make. If you go to the final project submission, you'll see the rubric for it and all of the criteria that are expected. So you see there's only 2 boxes, so it's a long list of things that I'll be expecting to see in that final project that you work on for 6 weeks. And they're all just yes or no check boxes, like yes, the vectors were implemented, or no, you ended up not making a software build for some reason or another. That might be a good place to start looking, even though that's not the one posted in this module, but that's a great little list of all the requirements that are expected. So if you think of the idea for a game you want to make, you can kind of go through that checklist yourself and make sure you feel like everything's going to be there. Otherwise, for this week, once you have an idea, you're just going to write up, tell me what it is. In the real world, I'm not a big fan of templates. That's just personal preference. I don't care much for templates, but in a classroom, templates are great. That document tells you what to write and where to write it, shows you nice formatting, suggestions on what to put, what little extras to put in there. So I like to do that for final project proposals. It's a great way to learn how to make them. So just Google like a project proposal template. Well, make sure you put free in there, because there's a lot of them that are not free. Free project proposal template. You can find a regular software development sort of project, but there are also game project proposals. So you can find some of these and just find a template that you like, kind of go through, fill it out with what you plan to make and the schedule and all of the things that are going to be in your game by May 11th, 11:59 p.m. So that'll be the final cutoff, right? So time constraints, that's basically a month and a half from now, right? You know, a month and a half to put together a big game. It's going to be very similar to your project, to your weekly projects, just with more levels and a couple other extra requirements I did already receive the question when somebody was having a lot of fun making the first individual project and asked if that could just be extended to the final project. And I was, yeah, that's perfectly fine. So one of the other games that we make through this semester just really catches your interest and you want to build that into something larger. There's similar requirements, going to have a cutscene to introduce the story, cutscenes for success or failure of the game. The homework assignments are all one level, and I think the final one needs to be 3 levels. So
it's 2 right there.
oh, is it two levels? Mine backed off from 3. So yeah, and then there's more extra criteria that we want to work in, make sure exists in that game somewhere.
Individual projects are there?
There's 2 individual projects and 2 group projects, but one of the individual projects is going to be a simulation of a pool game. So it's not, there's not necessarily a whole lot of expansion on that. That's why we're really going to dive in and practice physics. So we're studying physics and physics materials this week. Our collisions in depth with physics in mind next week. And then we'll do a big formal proper simulation. So that's what's coming up. Yeah, and remember, it's check that rubric. It's actually in the module 8 page for the final submission, but that shows the checklist of everything that's expected for your games. Make sure you feel like your idea is going to be able to check off everything on that list. Any questions about any of those things? The other big assignment that's due tonight is the spreadsheet animation. I've already got quite a few. I think about half of you all have already turned them in. Are those going okay? Any issues? I see head nods here in the classroom. Hopefully, similar thing on Zoom. But yeah, the ones that have been turned in are looking great. And yeah, there's not quality criteria. I'm not evaluating your artwork. I'm just evaluating your ability to make a spreadsheet and make sure that when I go to grade it, I'm going to load it into Godot, make sure it loads up the thing and plays to the brain like it's supposed to. The actions are separated and easy to work with. And there's some more stuff we'll do with those spreadsheets later. Oh yeah, that's another thing in the final project. One of the animations has to be included. We'll do the spreadsheet animation, that's due tonight. In a couple weeks, we'll have a skeletal animation, or a 2D skeletal animation. And then in module 6, we have a 3D skeletal animation. And at least one of the animations needs to be included in your final project. And the one will be used in the module 7 discussion board when we set up look at the process for setting up accounts on itch.io and Godot Marketplace and selling game assets. This is one skill set we don't have to wait till much later to start monetizing. It's actually really nice whenever you're making a game. Every time you make an object, make at least 2, and then sell one of them, or keep the best one for yourself. Sell the other one for other game makers to work with, and that can help bring money in during the long stretches of time it takes to put a finished game together. You don't necessarily have to wait till the end. Okay, I don't see anything in the chat for questions or issues with the spreadsheet. So I assume that's going well. The ones that have been turned in are all looking great. So in module 1, we started talking about physics because we needed it for our first example. So, but there's a little bit more to talk about. So that was sort of a preview of it. And a lot of the physics are built into that physics engine. We've talked about this before. The one thing we have to have from the physics engine in a game engine is the boundary, the collision shape, the interface where physics occurs. that's the only thing we absolutely have to have. And it just so happens that people have been building coding libraries for quite some time now. And they continually add to the physics library, and most of the laws of physics, as we know from the real world, are already programmed in there. They're ready for us to use, and we just need to know kind of when to use them. Sort of an intuitive approach to it, which is going to fall back and start with Newton's three laws. First law is the law of inertia. That has to do with movement. It's usually stated as an object in motion will remain in motion unless acted on by an outside force. All right. Sometimes it's extended to include in a straight line because if there's no other forces acting on it, there's nothing going to turn it or anything. It's just going to continue in a straight line forever. Also stated as an object at rest will remain at rest unless acted on by an outside force. It has to do with mass. Once something's moving, it's going to take a certain amount of energy to stop it. Inertia is what really got the astronauts in the space program back in the 60s, because they knew how much lighter things were going to be. They knew things were going to weigh less when they got to the moon. So they used pools and manipulated the buoyancy in the suit just to try to replicate what the weight was going to be. But they forgot about one little thing, and that was inertia. So if you ever saw videos of the astronauts when they landed on the moon and would be like falling over backwards and doing backflips and stuff, yes, it was lighter and they were used to carrying it. So if something was like 180-pound backpack on the moon, it's 1/6 the weight, it would have felt like 30 pounds. But when they start walking, it's still like stopping 180 pounds. So that's what was throwing them off. It takes just the amount of energy to stop it once it's moving. The law of inertia. The second one is just a math equation. A force is mass times acceleration. That's how we always find it. We control things by force, using force. When we were in preview mode in week 1, we saw we have a apply force and apply impulse. But like in our cars, to control things, there's only one value we can change. We have the acceleration or the brake pedal for negative acceleration. And when we turn, that actually creates a rotational acceleration. All probably experienced it in class when a car turns sharply to the left, everybody inside that car gets pushed to the right. I think everybody's experienced that at some point in their life, or vice versa. And so when the wheels start to turn, that's not really what turns the car. What turns the car is that change. The wheels are trying to make the car spin around, like do donuts over and over and over again. And friction prevents it from going too far, but when it starts spinning, it gets the sideways force that pushes it over. That's a small, subtle thing, but when you're programming your game, objects in your game, you need to keep in mind that it's not like suddenly turning a different direction to make something move in a different direction. The turning gives rise to a rotational acceleration, which then applies to the given mass that we have and creates a force pushing one direction or another. And when you go to code that, you will sometimes get that thing like the effect like in the car. If you just try to turn it and trust it to go straight, it's like when you're sitting in the car and the driver turns the wheels sharply to the left and you get thrown up against the passenger side door from the, well, actually the result of Newton's third law. equal and opposite forces. For every force, there's an equal and opposite force. And it's actually the equal and opposite force that we experience. That's the one we feel. And gravity is pulling me down on to the ground, but what I feel is the ground pushing up against my feet. When the car turns to the left and we get pushed to the right, right? The actual force is pushing everything to the left, but what we experience is the equal and opposite one. In our games, when two things run into each other, they're going to bounce off each other. Right? Two moving things collide, bounce backwards. So there's always two forces to keep in mind, and multiple things happen with everything we do is the big thing. So sometimes when we're coding, putting together the code for our games, we might get some unintended consequences from those equal and opposite forces. So keep an eye out for those. But the three laws of motion, so pretty much they're there for us to work with, and we just have to know when to use them. The computer is going to do all the calculations; they're already built into the physics engine. Unless we're writing something with entirely new laws of physics, we don't have to do any of the calculation ourselves. We just ask for the functions. And remember to, like when you're driving your car, you always want to control acceleration. The acceleration is the thing you have control over. We talked about this briefly the first day because we needed it in our code. There's an expansion on Newton's second law of the force mass times acceleration. Is this, there's no time involved. But in the real universe and in our game engines, time does come into play. So impulse is force per time interval. So amount of force over a change in time. I can probably zoom in closer to the board to make that easier to read. Standard example of this is we want to stop a car. We got a car moving along at 50 miles an hour or something. Draw the car, it's moving along at highway speeds, let's say 55 miles per hour. And in order to stop that car, we have to apply a force. Let's consider an outside force, right? Not the brakes, the car, so like a car wreck kind of stopping it. This mass moving at this speed is going to take a certain amount of force to stop no matter what. But there's different ways we can apply that force. We could hit a brick wall. That's going to stop it pretty quick, right? Probably total the car, completely destroy it. Or we'd hit like a little row of bushes. A row of bushes will also bring a car to a stop. So it must be applying the same amount of force. It's just doing it over a much larger time interval. So hitting the brick wall is probably going to destroy the car and everybody inside it. But hitting the row of bushes is going to scratch the paint a little, even though both methods apply the same amount of force. So we want to take that time into consideration and consider impulse when we're coding our games. Impulse continually happens over time. We'll see the difference when we get to some examples. Because to move things, we can apply a force or we can apply an impulse. And the force doesn't take time into consideration. It just applies the force and keeps applying it. So it will continue to accelerate forever. But the impulse sort of breaks it up into the time interval like we have in our frame rate stuff. We get a difference between them. I still on board. I should move the camera over a little. Roll over a little. A couple other things just to take note of here. Gravity is going to be coded in. Gravity is an acceleration. We can tell that really easy, right? I'm holding this marker here. Has a velocity of 0. And if I let go of it, the velocity changes. So it has to be an acceleration pulling on it. This one you might need to punch in a calculator periodically. The physics engines by default is going to be using the metric system. So gravity is pulling at 9.8 meters per second squared. Actually, it's 9. It moves 9.8 meters per second faster every second. And we usually write it this way. We don't necessarily need the units. That's about 10 to make our math easier. Because this is one you will have to, as you're putting things together, maybe pull out the calculator periodically and be like, okay, I need to put this number in the box. And it's an acceleration. So something like weight character is whatever its mass is times that acceleration from gravity. So if we have, say, a 70 kilogram person, it's 2.2 pounds in a kilogram, so a little bit more than twice as much. So 70 kilogram person is going to be about 160, 155, 160 pounds. But that multiplied by gravity, or this thing 10 is easier to work with and will be enough for getting our estimations. It's going to give us 700, and technically the equivalent of pounds is newtons, would be the units. Kilograms actually measure something different than pounds. Kilograms are a mass, just how much stuff is there. So weight of 700. So if we wanted to say make our character jump, we know that gravity is pulling down on that mass, creating a downward force of 700, whatever our units are. This is a physics class. We don't need to dive into them too much. They're labeled on the GUI we're going to use. Pulling down with 700. So if we want to jump, we're going to have to push with more force than is pulling us down. Right? And then how high do you want to jump? Because if you just want to barely get off the ground, right, we can do 710. It's going to lift it up, but we'll probably barely see it wiggle in the game engine. So this is one that you might have to plug in a calculator occasionally, and it's going to show up in our example today. So you can see where it is, just for determining how much force you need to overcome in order to do certain things. 32 feet per second. If you're curious about that, since we're Americans, and might not have much intuition on what 10 meters is. About 3 stories, about a 3-story building, 32, a little over 32 feet. Faster every second as time passes. And the last thing I had on the board notes, for the board notes here, is something to keep in mind is conservation. Put a little line to split things up. There are conserved quantities, things that will never, whatever we put in, we get out. So energy and momentum are both conserved quantities. If we put in a given amount of energy to a system, that amount of energy is going to stay there. That'll come into play when we do the pool game simulation in module 5 and 6. It's when we move the cue to hit the ball and send it rolling and hitting another thing, that movement that we put into the stick is the only amount of energy we're adding to it, right? All the pool balls were already sitting stationary. So we add that much energy, and then that becomes momentum, which for calculation is just mass times velocity. So stuff moving is what momentum is. Once stuff is moving, it becomes conserved. So in the pool example, we move the cue stick, that introduces energy, and then that starts the cue ball moving. And when that cue ball hits another pool ball that will have the same mass as that, afterwards, there's still the same amount of movement. Mathematically, it's going to look kind of odd. I'm going to write M1 times V1. So the mass of one cue, maybe the cue ball, is moving at a certain velocity after we hit it with the stick. Plus the mass of another one of our pool balls, if we multiply that by its initial velocity, which is going to be 0 because it's just sitting still before the cue ball hits it. Afterwards, our masses don't change. So we could still add that back up. The mass is just the amount of stuff there. But our velocities, I'll put a little asterisk up here. Our velocities are going to be different. Right? All of the movements in the cue ball, maybe the 6 ball is stationary, but when the cue ball hits the 6 ball, the cue ball is still going to be moving along a little bit slower, and the 6 ball will be moving faster. But if we took and added it back up, it's equal to the amount of movement we had before the collision. And it'll be pretty close. In that particular example, there's some energy given off to sound, some energy becomes sound, some energy becomes heat. So it gets really, really complicated, and depending on the game engine, some of that stuff might be worked in. But in our simulation, it's going to be really, really close. So movement is a type of energy, kinetic energy. A similar thing. There's a certain amount of movement in a system, and we're going to end with the same amount. So if move kinetic energy, example of the pool cue ball hitting another pool ball, it hits, and then in that collision, there's like friction that produces heat and sound that comes off. And there's a lot more stuff to measure there, but if we measured it all up, it'd be exactly equal to the energy of that initial cue ball moving before it hit the other ball. And that would be also equivalent to the amount of energy we introduced when we hit the cue ball with our stick. So we don't have to do the calculations. We just want to keep some of these things in mind. This conservation of momentum is another one that you'll have to watch out for with unintended consequences in your game. You'll focus on 1 or 2 game objects and start programming it. And then when the physics runs free, those conserved quantities have to go somewhere else in the game, and it may cause little issues. And like what we were talking about earlier, just the things to watch for. This is really the only calculation we'll need, and then for that, we just need estimates, kind of give size estimates on how much force we need to use in a certain place. Any questions about that? The game engine is going to handle most of it for us. We just need to know when to put it in, and some of the terminology, because that's how the game engines all name the things with that standard terminology. I'll fix this in a while. Okay, so there's one more section of board notes for later, for when we get into probability. But let's start, taking a look at what we would do when we go to put this in our game. The stuff's built in. It's very, very easy. You'll see the reading assignment this week. I'll talk about this as we go through. So let's go ahead and start a new project in Godot and kind of walk through some of this. Yeah. I'll just create a new project. I haven't deleted them in a moment. None of these examples so far have really been worth. They've been small things, but new project number 4. You might want to give it something meaningful, a meaningful name like physics or rigid and static bodies is really what we're looking at. Anybody looked at the reading assignment for this week? Yeah. Guessing no. Everybody in the classroom looked away when I said it. Probably a similar thing on Zoom call. Yeah, it's so I guess the last week's homework's not due yet, so it's not time for the reading assignment. Oh, that reminds me, on the quiz, I think I caught all of them. There was one question that I missed. It was a bad question. None of the answers seemed correct. And I guess I overlooked it whenever the AI generated all the quiz questions off the reading and said, which of the following is not a vector operation? And all 4 of them were math operations that we can do with vectors that were clearly stated there. So it was a bad question. Everybody that answered that so far, I just put the point back on it. Yeah, I do go through like the quizzes every single time, look at multiple submissions and stuff. Everybody that answered that so far, I put the point back on there and removed it from the question bank. So anybody that hasn't taken the quiz yet, or knowledge check, it's very low stakes. Word quiz is alarming. Anybody that hasn't done the knowledge check yet, that shouldn't get that question. There's also one about linear interpolation that we'll talk about later. The standard function name for that is LERP, L-E-R-P. Linear interpolation is filling in the gaps between. So it's like keyframes in an animation. Our characters in one position, and then maybe 5 frames later, the character's going to be in a different position. The computer is going to interpolate everything in between. And most often done linear, which means it's however many, it divides up evenly. So in the case of 5 frames, each frame goes through 1/5 of the movement. That's a LERP function. That question was in there. Anybody that missed that question, I'll put the point back on it, and just wanted to mention it because I overlooked that question because we are going to talk about that in around week 6. We're going to talk quite a bit about linear interpolation, but that's later in the semester, so I'm not sure how it ended up in the module 2 question bank. Otherwise, the quizzes look good for this week. Let's see, let's find these. Video. Oh, that's the wrong one. Controls, there we go. So I did turn the controls off on my laptop. So if anybody, if something shows up in the chat, somebody please let me know. I don't see it. I'll try to keep an eye on that screen, but I turned it off on my screen here. So let's do 3D scene. One of the nice things about this engine is 2D and 3D are handled the same. So we can create a new 3D scene. Start with a blank node. I'll just call it world. So the little world we're working in. And I think we need some places to start walking around on. So I'll add, well, we talked about this before. The things that hold physics are our bodies. So we have a rigid body, rigid body and a static body. We also have a character body, but character body is unique for, we want to generalize this knowledge. And character body is designed to be controlled entirely through script. So most of the physics are turned off on that. But if we use regular laws of physics, the controls the player experiences are going to feel a lot more comfortable, a lot more natural, because they're hitting buttons and getting responses like they would in the real physical world. So the player's natural intuition kicks in. So a static body has all of the laws of physics except basically gravity's turned off. It's locked in space. It's something that doesn't move. We assume it has just huge mass. So like even if a 70-kilogram player comes down and hits it, it's not going to bounce. It's like the Earth, right? Technically, back to Newton's laws, there's an equal and opposite force. So when we jump up and come down and hit the Earth, momentum's conserved. Our velocity goes to zero. So technically the Earth moves, just not enough that we would ever notice it. So it's kind of like that. That's something massive that's not going to matter when our small game objects hit it. It's locked in place. And we've seen before, we need at least 3 components for everything we put in a game. That'll be our logical body. So if we need to do any scripting on that. There's also an animatable body that when we have a static body that we do need to move some. So think of like a platform that moves, but it's never going to like fall away or respond to any physics interactions. It's just moving back and forth. So an animate, but all the ones that have body in there are laws of physics. Start with a static body just for the ground.
Rigid body is the one we should use instead of character.
Yes. Yes. Rigid body, and then there's actually 2 variances on rigid body we'll get to here. I think in about 20 minutes. But a couple things before we get there. Rigid body and kinematic body. The subtle difference between them, but those are also ones available in all of our game engines. So static body is going to be our logical body for the ground we stand on. We'll also need a graphical body. So in 3D, that's going to be a mesh instance 3D. You start searching for that. Or graphics go. And then we'll need the physical body. That one thing we absolutely have to have from the physics engine. The boundaries, the collision shape, the area around it, or just the interface where it interacts with other physical objects. So I'll select the root, the static body for the root, and pull in the collision shape. Now we can start filling this out, maybe rename some stuff. So I'll call this the ground. Make it easier to keep track of. And remember, when we get to coding, we do have drag and drop options from this stuff here. We can drag this and we can just click and drag that into our code. So it's really good idea to go ahead and name it first, so that you're ready to add it to the code and you don't have to come back and do a bunch of renaming stuff later. For the mesh instance, like always, if we go over to the inspector panel, there's something near the top that says empty. That's what we need to start with. So just what is the mesh we're putting in here? Let's just go with a new plane mesh. It's our ground, so that's just a flat surface. We don't need any depth to it. We're going to stand on top of it. If we click on it again, we'll get some more options like the size. It starts at 2 by 2. Let's make that 20 by 20. So a nice big thing to work with. And then right down here, you'll see a material. You come down to the material, that's like our color in 3 dimensions where we have to control the lighting as well. The we need more information than just what color is it. They're say whether it's smooth or how shiny is it? Is it dull colors? In transparency, metallic roughness, how the emission, how does it reflect the light, occlusion, how does it absorb different wavelengths of light so that when light reflects off of it, it does different. Quite a bit of materials that we can get to. You will want to keep an eye on this because when we look at shaders, this list right here is the keywords that we code in our shaders, and that's when our material is dynamic and changes with time. Albedo is the color. So if you go to, let's just make this green for now. If you go to albedo and choose something green, and this is an odd one in Godot. The thing is set all the way at the full brightness, so just the white overshadows everything. It's HSV colors or about the RGB. You can choose any of them. I'll go to the HSV tab so you can see that it's set at full brightness, so it's like the room where this color is existing is so bright we can't make out what color it is. So you want to click somewhere in the middle so that you can see the differences in the colors. Oh, yeah, you usually just click somewhere in the middle, and this is grass, so go somewhere green, something greenish. That'll work for now. If you want to, maybe mess around with the metallic values, turn down how much it reflects, and turn the roughness up quite a bit. You can add new textures. There's a lot to that. We'll look at that in small sections throughout. But I guess the big thing to remember is albedo is the color we actually want. And that color I picked looks really strange on the TV across the room. It did not look like that on my laptop. When I looked up, I was like, whoa, that's that color dies a little. So that'll be our ground. Oh, well, we need a shape, the physical shape of it. And we did a plane. It's just a flat surface. If I spin around some, you can see there's no depth to it. Or if we look straight from the side, we can't see it at all. It's just like the one side. So for a shape, you notice we can't have, there's no option for a planar shape. So we just go with a box shape and then set it to the size it needs to be. We know our ground is 20 by 20. And remember that's XZ. The Y is the vertical. So we set X and Z 20 by 20. Should see the blue lines kind of show up, and it's a very flat surface, so we can just make that very small. 0.01 or 0.1. I guess would be 10 centimeters thick. And that gives a physical shape to it. So we can interact with it, we can see it, and apply logic to it, though in this case, the logic is just it's a static body. It's just going to sit there. Now we can do the more interesting with the rigid body or kinematic body. So go back to the root of the scene, the base of the world, and search for rigid body 3D. There's our logical body. That's what our script will attach to. That's what our script will normally attach to, but what we're going to look at today is in the inspector panel. So we're going to look at different things happening in the inspector panel. I don't know if we'll get to actually scripting things, but these are all of the properties that we interact with from our script. So there's our logical body. We'll add to that a graphical body, which is a mesh instance for 3D. And in 2D, we can either do a mesh or a sprite. Otherwise, 2D and 3D are very, very similar in this game engine. And we need the physical body. So collision shape. 3D. I'm gonna call that object for now, just in case we need that word to refer to that. For the mesh, there's a couple options. Square, just cubes are a fairly common starting point. A lot of people like those. Cylinders and capsules have a player size, so it's kind of what it is. I'm going to go with a capsule one. It's like a cylinder that's rounded off at the ends. If I move it up, you can see like a cylinder rounded off at the ends. So the default size, if we look at the default size, and this is consistent in all of our game engines, is it's about a 1/2 meter radius and 2 meters tall. So a little bit bigger than what a human would be. A lot of people really like those for the starting points. It gives us a good idea of where our final draft of the character model would be if it's a human shaped character. Really, the average height would be like 1.8 meters tall, and 0.4 meters radius would be a little bit more closer to the average height, which actually that's met. Yeah, that's 5'11", and a little less than 3 feet wide. Measure the shoulders. But I'm just going to keep it for the default settings for now. Set that up. Then our collision shape, there's a capsule collision shape. Oh, come back here. Because I moved that up. So I'm going to come back to the transform data and reset that. And we'll adjust that in a moment. And the collision shape, we can use a capsule collision shape, and that'll just wrap nicely around that. But it seems to be in a weird spot, right? For our parent object, it looks like everything's right there at the origin, 0, 0, 0. But for the capsule graphics and capsule physics, it centered it instead of putting it under the feet. So I'm going to keep the logical body there at 0, 0, 0, right on the ground. And I'm going to go to the mesh instance and just move that up. So if we go to the transform, well, it's 2 meters tall, so if we move it 1 meter up, it'll sit. The bottom of it is going to sit right at the origin of that. So see where the origin of the logical body is versus our graphical body. Same thing for the collision shape. We can just move that up. Go to the transform, move it up by 1. Or if you go with a different size to be more accurate, to more accurately portray a human, like 1.8 meters tall and 0.4 meter radius, you just adjust it by half of that. So this is where our script would go and stuff. And notice over in the inspector panel, we have a whole lot of things about physics. So what the mass of it, gravity scale. So this is in G's, the way we would normally hear it. So right there it says 1.0. So that is 1G, which is just the gravity when we're standing on Earth, or this number here, 9.8 meters per second. But when we need that, an estimation is going to be close enough. So maybe think of that as 10. You can move that up or down. So if you wanted like the moon's gravity, well, that moves a lot. So you probably want to type it in 0.333. Yeah. You type in 1/3, that's not 1/3, it's 1/6. 0.157, something like that. And get the accurate gravity for the moon. I'm just gonna leave it like we're on Earth. And look at some of these other things. So I'm gonna expand all of these, the mass distribution. So what, like, where is the center of mass? Like, this is the one that gets really odd, can get really tricky on a human shaped character. You probably haven't thought about it in a while, but probably at least have an idea of how long it took you to learn to walk. Humans have a really, really odd center of mass. We're constantly adjusting things. Our muscles basically never stop working for little adjustments. And when we're young, it takes us well over a year just to start standing up and moving, right? A very odd shape to move around, and then it was probably several more years you would just kind of randomly fall down, or actually that often happens to us throughout our lives. We just lose our balance and can't get and end up on the ground because the mass is centered in a really weird spot on our bodies. It's not symmetrical like that thing on the screen right now. So we can adjust that. So I'll go ahead and hit run. Oh wait, before I save it. Right now that thing has a nice center of mass, so gravity's gonna pull it down, sit on the ground, and it's gonna do that, but oh, we need a couple more parts before we can see it. In 3D games, we need light and a camera. It's not already set up for us. We'll see how to set them up before long, but there's light. The light and background environment stuff here is just a preview. That doesn't actually come into our game, but if you click the little 3 dots here, you can add those to the scene. So we're ready to kind of make our own world environment and the directional light. I'm also going to move this up off the ground a little so we can see physics pull it down. Oh, I forgot the camera. There's no camera, so we have no way to see it yet. So I'll attach it to the world, and then we'll just watch from a distance. And this is probably a good place to look at it. If you look at the little camera icon there, and or we can see where by default the camera faces. So the engine is set up so that negative Z is our considered our forward direction. So I'm just going to move the camera back and up, maybe rotate it down a little so we can see a large section of our little plane here. So you can see it fell down, and the computer detected exactly where the center of mass was. So even though there's a rounded bottom, it's perfectly balanced. So it's not going to, back to the law of inertia. It's at rest. So unless there's another force come along and act on it, nothing's going to happen. But come back to that rigid body or object. If we set our center of mass somewhere, so let's come like 0.2 in the X, 1.1 in the Y, and 0.3 in the Z. So that's a spot a little over halfway up and off center in the thing, so it's no longer balanced like it was. It's probably balanced more like a human now. They just hump, right? It can't stay perfectly balanced because just where the center of from where gravity is not pulling from the center anymore. So it kind of goes off the side. Depending on the level of realism you want in your game, you might want to adjust that. You can adjust the inertia. So like that's how much extra resistance is there in each direction. So maybe and the X put in like 1 kilogram of resistance in the X and Z, so we have to push extra hard to get it moving or to stop it from moving. I'm just gonna hit reset though, just kind of talk about what those are. I'll reset that to this nice little center one, or we might come back and click on some things. Deactivation is for turning it off. What's it do when the player stops controlling it? Or when the script stops controlling it? Maybe it's an automatically controlled thing. You can see freeze mode. Under freeze mode is either static or kinematic. Static, when it's like the player stops control, if the player stops controlling it, it's going to act like a static body. Or if it's script controlled, when it hits a spot where the script stops controlling it, it's going to act like a static body. It's just stationary in space. A kinematic freeze it's stationary in space, but the laws of physics still apply. So if something bumped into it, it's going to fall over. It's going to fall over and respond to it. So obviously, we probably want most of those to be kinematic, but also notice right above it is freeze is not turned on. So it's you'd have to turn that on and then set it to kinematic. Like when it's not being moved, how does it behave? Oh, there's deactivation. This little section under solver is a little bit different. Really the one that's going to show up early. Custom integration, contact monitor, those are getting a little more advanced. I guess we can hover over it and see what it is. Hey, hover your mouse over it, you can see what it is. If it's true, the standard force integration will be disabled for this body other than collision response. So it can't initiate any physics. It can't run into something else, but something else can run into it. The second one down though, this is continuous collision detection. Our physics engine and our graphics pipeline do not run at the same speed. By default, the physics engine's at 60 and the graphics frame rate is probably at 140. They're not running at the same speed. So it's possible that our code might not check at the right time and will pass through objects. I think that was happening to you, Josh, in this when we did that first example in week 1, right? Sometimes when it started getting really fast, it would just pass through the wall because it wasn't checking at the perfect right instance. And checking that box adds a lot of RAM usage to your game. So obviously it's like, oh, well, that sounds like a great box. Let's check continuously. And that way, even though our script and physics engine might not line up time-wise, remember we talked about frame rates and getting glitches and stuff? That's not the case for physics engine. The physics engine does need a hard-coded frame rate. It needs to be the exact same thing every single time.
But I guess also if you make it so that stuff can only go up to a certain speed.
Yeah, that's an option too. Yeah. There's different ways, but they don't perfectly line up. So it's like, oh, continuous collision detection sounds useful, so then we don't have to worry about them lining up. But that adds a lot of RAM, takes a lot of RAM usage, because that adds a whole lot of things to make those line up at every millisecond, basically, instead of 15 or every 10 or 12 or 16 milliseconds. So if you're having a problem where your character occasionally passes through walls, because you get moving too fast and it didn't check at the right time and you already passed through the wall or the ground or something before it detected it, then there's that checkbox to handle that. And then this is monitor, we can just add more signals, triggers, and that's what we're gonna look at next week. So just remember, if you wanna start making custom signals that go out, check that contact monitor box. Then we have linear and angular velocity. So linear velocity is in a straight line, angular velocity is rotating. And think about it as rotating around. So the angular x velocity is, like, the x-axis is the red one. So that's like when I grab this red wheel and spin it, the speed is going there. That's the angular velocity for x. So spinning around that axis. Got so you can see the physics fall. So let's give it some linear velocity. If we spin it, yeah, we won't be able to see this spin very well because really the only thing we could do is rotate around the y-axis, but it's very, very symmetrical. We just plug a number in there. So in our z, negative z is forward. So if we say, let's try some numbers. Negative 50. When we run it, it should start moving pretty fast. But like, it definitely overcame gravity when we applied a force that direction. Let's try like negative 10. So it just kind of tumbled down, and there's still a negative z acceleration, but now negative z forward for that object is down into the ground, so it can't go any further. Right? These are things we would code, right? So in your code, you have like linear velocity. There's, yeah, just hover over it. It shows the shows that, and then dot. So velocity dot z, because oh, we don't have a script to it. File the script. I'm not going to attach it to anything, because when we're over in our scripting tab, we can grab and drag that in. See, it's linear velocity as a tag. If we right click on it and copy property path and paste that in, that's the variable name for it. Linear underscore velocity dot z equals 50. Or we have negative 10. So that's the equivalent of what we just typed in that box here. We put it in the inspector panel when we want to always control it, and then add it to the script when we start doing other things with it. Let's see what negative 2 does. Getting smaller and smaller and smaller. You know, but you might also notice that I skipped over the very top box on the inspector, right? Let's go back to 10. Linear velocity of negative 10. Since it's shooting off pretty quickly and tumbling, almost falling off the edge. If we went one further, we'd probably tumble off the edge. But up here, our top box was max. It was saying it's 1 kilogram. 1 kilogram is 2.2 pounds. That's not very much, right? It doesn't take months to affect a 2-pound thing. And that's something small. I'm pretty sure this is less than 2 pounds. But this remote here, it takes almost nothing to move that around. It's very, very very light, weighs almost nothing. Power supply has a nice size transformer in it, so it's got a little bit of weight. And as we have, there's more substance making it up, right? The kilograms are mass. How much stuff is there? And it's not equivalent to pounds. In empirical system, there's a unit called slug. That is actually the equivalent of a kilogram. And then that unit times the amount its acceleration give the thing is accelerating will give us the weight of it, the full pounds like we normally talk about. But so kilograms are something different. That's just how much stuff there is. 1 kilogram is pretty small. This is like the shape size of a human. So we'd probably be up around like 75 kilograms. That's a 180-pound person, coming on 180-pound person. 2.2 pounds per kilogram. So 75 times 2.2. Oh, that's 160. So 160-pound person. So now that there's different forces of the forces apply differently to it. So, but notice this is just the velocity, not the acceleration. So normally we don't have any control if we start working at velocity, right? That's just saying this moves at this speed, but it well, we can see it doesn't look natural, right? It starts coming down, but then it's going forward as it's going down. So it's like we started watching when it was already moving. So normally we wouldn't really mess with those much. But a couple of them you are going to set. So that mass, you're going to want to set that every time, because then when we go over to our script, like we saw the other day, and run that apply impulse, right? Whenever we run our apply impulse thing to start putting forces on it, it's going to make a big difference depending on how much mass there is. Likewise, things like friction. The amount of friction is based off when it pulls down and moves forward. Maybe if I put a slow velocity here. Put a small number and creep up on that. So notice with 1, all it did is it tried to move. It couldn't overcome friction and just threw itself off balance. But if the mass was really low, let's set it back to 1 kilogram, we can make the same here. And let me try to find the number. Oh. The number where it just barely starts moving. What's 0.5? Okay, so it's falling really, really slow. To the mass of 1. So if we increase that to a more realistic mass, there's going to be a lot more friction from gravity holding that thing on the ground. Oh, it still fell. I was expecting it to not fall that time. But at some point, y'all are going to want to go through and click on all these. And I just looked at the clock. Sorry, I didn't realize that so much time had gotten away from us. So probably should take a break. But you're going to go through and just kind of click on those boxes, make little changes, make sure you understand what they're talking about as those things apply. The velocity, you want to be careful with that box or using velocity in your code, because it's just always moving at that speed. You have no control over it whatsoever. You can't change it to make things happen, and you can't pull forces out, because if you put a constant velocity, what's the acceleration? If velocity is constant, then acceleration is not then it's not changing speed. So our acceleration will always be 0. And if we plug that in to this equation up here on the board, right, any number times 0 is 0. So if we have a constant speed, we cannot apply forces to other objects. So you want to watch out for those boxes, and they are included in like all of our gauges. But I just looked at the clock. I probably should have took a break about 10 minutes ago. Sorry about that. 10 minutes break time. Break sound good. My throat's getting really dry. I should have noticed that. I've been talking for quite a while. How dry my throat is. I could definitely use a sip of coffee. So, my laptop says 3. Oh, no, that's the date. My laptop says 2:22. So we'll get back to it at 2:32. See y'all in just a moment. I'm gonna go get a sip of coffee.